All right, peeps, here we go. Let's party on down. We've got 2.3 flows of energy and matter. We're not getting it through all in one video here. It's just not really feasible, not what we're going to get done. Define insulation in your own words. My words are for define insulation if you're listening to me, incoming sunlight. So that's simple. The amount of sunlight that's coming into the world. Reflection plus absorption. Some of that sunlight is unavailable to animals and humans. So darn right. So not everything that comes in for sunlight is going to get absorbed by green and leafy plants and animal plants. All right. So if they're not absorbed by plants, animals can't use them. So some is reflected off the ocean, some is reflected and absorbed by rocks, like different things. Not everything that comes in is actually usable. Energy transfers for ecosystems include light energy to chemical energy. Photosynthesis. Yep, light comes from the sun, gets absorbed by these green plant leaves. We use it, transfers it off to glucose, basically with photosynthesis. Transfer of chemical energy from trophic levels to trophic level. A crap ton of energy is lost. So what happens is green leafy vegetable, right? Comes along. Squirrel eats it. All right. Absorbs that energy. Some of it is lost, though. Actually, most of it is. The bear eats then the squirrel. Okay. So, yeah, energy is lost from going from like the leaf to the squirrel, then to the bear. And then we go and shoot the bear and eat bear burgers. And we're at the top, and even more energy is lost. So, when you look at the amount of energy that's lost between green leafy plants and goes up the chain, it's quite a bit. So, convert UV plus visible light to heat energy. Let's see about this. So, yeah. So, obviously, light comes in, whether it's UV light or even visible light, it's going to hit a rock. It hits a rock, it absorbs by the rock. The rock then lets off heat. Yep. Re-radiation of heat to the atmosphere. So that's heat can get trapped in via greenhouse gases, but also too with clouds and water vapor. Definitions. These ones are muy importante. All right. Definitions. Productivity, transfer of energy, usually food into biomass, size for amount of time. So productivity is you eat and then you gain size. Some of that's good. Think of like a teenager growing up big and tall. We like that. Some of it is me eating too many Christmas cookies. Not so good. All right. It definitely gained some biomass come Christmas cookie season. But also too, if that animal wants to grow, it's going to need food. So, net primary productivity, NPP, is the gross primary product, GPP, minus the respiratory loss. So, the equation looks like this: NPP equals GPP minus R. So, the respiration is like the things you do just to live and survive. The amount of energy you need to come in just to be a freaking couch potato. Yep. Gross secondary productivity, GSP, equals food eaten minus the fecal poop matter loss. So you'll find out later on, elephants that eat all day and they crap all day. Yep. Interesting enough, lions only eat once in a while and crap once in a while. So, yep. Net secondary productivity, GSP minus the R. So, if you look up here, it's gross secondary productivity minus the respiration. So, maximum sustainable yield, NPP or MSP of a system. So, yep. Key points. All energy comes from the sun. I think I've drilled that enough. Everything energy wise comes from the sun. 60% of solar radiation is intercepted by our atmosphere. That's why our atmosphere is so important. We have one, the moon doesn't. If you notice the nightlife at the moon, it's not a happening place. Not really. So the atmosphere is what allows us to trap in heat, but it also protects us from the sun's rays. Otherwise, we just be getting bombarded with them and nuked. So, um, most UV is absorbed by the ozone. Ozone, very important layer. Increased UV exposure, increased cancer rates. Most infrared light heat is absorbed by carbon dioxide, methane, clouds, water vapor. Those are those greenhouse gases. They trap in the heat. It's like you wearing a blanket. All right. The greenhouse gases don't produce heat, they just trap it. 35% of sun energy that reaches surface is reflected back by ice, snow, water, and land. Glaciers matter because the more glaciers we have, they are awesome at reflecting that sunlight. It goes like coming down and goes bing and right off into outer space. And it keeps things cool. So, glaciers, very important. The fate of solar radiation reaching the Earth. Define solar constant for me. Let's see what if I can do to get on the right page here, people. Oh yeah, solar constants right there. So if you're looking, page 81, right fat in the middle. So that one might be easier with the Google definition though. Sunlight comes in and is absorbed by green plants. It doesn't get absorbed by, other plants, only the green ones. It allows life on Earth as we know it. Because without plants, we wouldn't have without mint, we wouldn't have mint chocolate chip ice cream because we wouldn't have the mint. But also too, if you didn't have like sunlight coming in giving us green grass to eat, we wouldn't have cows. If we wouldn't have cows, we wouldn't have milk. If the sunlight didn't come in and it wasn't absorbed by sugar cane, we wouldn't then have sugar to then put in the milk with the mint and make mint chocolate chip ice cream. So photosynthesis, it converts sunlight into energy. So it takes sunlight and transfers it off to chemical energy, glucose. So, yep, all that good stuff. Let's figure out where we're at here. Productivity. Oh yeah, for wheat, all that sort of stuff. Wheat's a very efficient plant. All right. The sunlight breakdown looks like this. Even though it's efficient, 5% of the sunlight that comes in, it like hits wheat plant. 5% of it's reflected. 50% of it's just straight up lost. 5% passes through the leaf, believe it or not. And then 40% is absorbed. Keep in mind that wheat is efficient when we say 40% is absorbed. There's other plants, they're not absorbing 40%. Nope, bunch of slackers. Out of that 40%, only the red and blue wavelength is used for photosynthesis, which is why we see like green plants because it's actually the part that's green we're not using, so that's the part that gets reflected. 31% of the sunlight that comes in is useless. 9% is actually used for photosynthesis. So what you have to figure out is what is the GPP. Remember up here, GPP is GPP gross. All right. Sorry. Thought I had the GPP. Gross primary productivity minus respiratory loss. So, what is the GPP? 9%. All right. 3.5 of this is respiratory just to stay alive. So that 9%, what is the NPP? It's going to be 9% minus 3.5, so that's going to be 5.5, I believe. So, yep. In general, the efficiency of conversion of energy from sunlight to food for animals is low. 2 to 3% for land, 1% for aquatic systems. Reason why is because like a lot of the water absorbs a lot of the sunlight, which leaves very little of it for seagrass, seaweed, stuff along that nature. Understanding gross and net is important for your paycheck as well. Tell me, oh, this should be in green here. Sorry, peeps. I'm going to need you to know that. Good. All right. Productivity. Actually, I'm going to leave that right there. Productivity is right here. Glucose or any other food can be used in two ways: life processes and new material. So, life processes, that's like the respiration stuff, things that we do just to stay alive. Energy is lost as heat. Even as you just being on the couch, being a couch potato, your body produces heat. That's why if you need to warm up some really quick, two people in a bed does it really fast, which makes that sound rather weird. But for hypothermia and stuff, if someone's out in the freezing cold, body heat is a quick way to transfer off heat. New material. Glucose can be used to build out that um, plant or animal to new growth, basically. Think about trees. When the first few years of growing, they need to grow fast. So a lot of that glucose goes towards new material. Plant biomass has two possibilities: dies and decays, is eaten by herbivores. That's the fortune cookie for plants, man. All right. They're either going to die and decay or they're going to get eaten. All right. There you go. Some ecosystems have higher NPP rates, biomass than others. Rainforest versus tundra. You don't have to be a rocket scientist to figure out that, look, you've got a bigger growing season and like more ability and more diversity in the rainforest than you do in the tundra. The tundra just does not really, it's not a hospital place for your NPP, the biomass. So, some plant biomass has seasonal changes. Trees in New England. So the biomass is greater in the summer than it is in the fall when you lose all your leaves. And also the trees kind of shut down in the fall. So net secondary productivity, NSP. Total all energy is transferred to herbivores. So, yep, plants grow. Net primary productivity. NSP is where the herbivores eat the plants. Yep, those darn rabbits again. Not all energy is transferred to herbivores. In fact, quite a bit of it is lost. Only food that crosses the intestinal wall is absorbed. Soluble versus insoluble fiber. So when you eat a Triscuit, you'll see that there's on the back, if you read fiber, soluble, insoluble. Soluble, it gets absorbed by your body, and your body uses it quite a bit more than the insoluble. The insoluble is basically a Brillo pad for your intestines. It basically goes through, grabs anything in your intestines and shoots it right out. So the insoluble fiber is still useful, cleans out your guts, but you'll hear this term as roughage once in a while, but not as useful as the soluble. All right. Some energy is used in respiration. You use energy just to be a potato chip, just your heart pumping, your hair growing, your body producing heat. Some leaves as urine. So, yep, some energy is transferred, and cows that eat grass and they just piss it out. So, the rest is stored as new body mass. So it can be fat, can be muscle. Real important is after you work out, try to get your protein in. 20 grams immediately after working out, then 2 hours later, 20 more grams. That will help increase your biomass because it'll repair the damaged tissue, which is your muscles. Energy not absorbed is poop. So, yep, whatever your body doesn't absorb, it just poops right out. So far from plants, NPP to herbivores has a ton of energy is lost. So, just those herbivores are not efficient. That's why they got to eat all day. Look at the animals that are vegetarians. They eat all day. Horses, they eat all day. Cows, they eat all day. Elephants, yep, they eat all day. So carnivores absorb 80% of energy of their food. So carnivores are more efficient. Poop wait out poop out waste 20% of the energy of their food. So look, a lot of what they eat, they absorb, and very little goes out as waste, poop. All right. Respiration, more while hunting. So yeah, they burn a few more calories while hunting, but they're not eating all day, which takes calories. When you only hunt for about 15 minutes out of a day, or half an hour, maybe an hour, leaves the rest of the time for those good old cat naps. If you're a lion, you like cat naps. More efficient, more than herbivores. Herbivores absorb 90% of energy of their food. Poop out waste 60% of energy of their food. So herbivores poop a lot more. Who spends more time eating, a zebra or a lion? Zebra. All right. And why? Because they have to. They're not getting as many nutrients. A lot of that energy is lost from the grass. Next question. Who poops more, a zebra or a lion? Why? Zebra poops more. Because it's a lot of that energy it can't absorb across the intestinal wall, so it gets sent right out in the poop. Flows of energy and matter, transfers and transformations. Transfers simpler, use less energy, are more efficient. The exact opposite is true for transformations, which are more complex, use more energy, less efficient. So, cycles and flows. Flows go in one direction, and I'm not talking the band. So, energy is a flow. It goes from the sun to the earth to the plants, from the plants to the herbivores, rabbits, and then to the carnivores, us or bears or wolves, and then it loses it as heat off to space. It does not go back to the sun. So it is not a cycle. Um, on the other hand, chemical nutrients like carbon, nitrogen, water, oxygen, all of these are cycles. So, which you should know about from 8th grade science, the water cycle and the carbon cycle, but might get into them if we have a little bit more time. Nutrient cycles. Chemical nutrients spend most of the time in the cycle in organic matter. Its time in organic matter is limited. So if you look at carbon, most carbon should be locked up in rocks or fossilized fuel. Very little of it should be in the atmosphere. And then, some small amount should be us, living our best lives as animals and plants. But most of it should be locked up in sedimentary rock. Where was I with this? Oh yeah, organic matter is limited. Movements of nutrients is different than movement of energy. So energy goes in one direction. Carbon does not. Energy transfers tend to be pretty quick too. Natural ones for carbon and the others do not. They take more time. So, um, nutrient cycles, we don't create or destroy them. You don't create carbon, you don't destroy it. Same thing for oxygen. So, your hair is made up of proteins, which are made up of carbon. Tell me about the cycle of carbon for your hair. So, yep, sunlight comes in. Actually, let's do this. Carbon's in the soil. Plants grow, they absorb carbon. We eat plants and we take in the carbon. Using that carbon, we use it to make hair. Hair, we get a haircut, falls to the ground. They put the hair into the trash. The trash then goes off to the landfill. The landfill is decomposes back into the soil, and then it goes back to the plants over time. Where is the carbon stored? In carbon or carbon dioxide sinks. These are terms you're really going to want because we talk about carbon sinks quite a bit later on. Organic and inorganic. So a carbon sink can be organic, plants and animals. It doesn't absorb as much carbon as other things, though, like fossils. Fossils were at one time organic, but inorganic sources of carbon are sedimentary rock and fossil fuels. Most of the carbon is locked up in sedimentary rock, and we like that carbon locked up in fossil fuels. Soil is another one. Seashells. Actually, the ocean is a big supporter of like how to lock up carbon, because what it does is it absorbs the carbon, and then your sea animals, like with the seashells, lock it up, and that's what they use to make their shells. And then the animals die, and the seashells either get eroded or become sedimentary rock. Atmosphere, a small amount of carbon should be in the atmosphere. Unfortunately, with us burning a lot of fossil fuels, we are producing a lot more of that carbon dioxide, hence carbon, into the atmosphere. So, yeah, hey peeps, we're going to start off next time with carbon flows, but that's about it for tonight. So, yep, good head start. Chapter 2, 3. Bye.